Welcome. We're going to begin this video with a little activity. The mean value theorem is considered by some to be the most important theorem in all of calculus. It's used to prove many of the other theorems in calculus that we use in this course, as well as further studies into calculus. So we're going to do a little activity to explore this. Graph the points -6, 4, and 5, -4 on the grid below. And this is not in your notes. It's just a little activity. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Come on. Yep, almost. And 5, 1, 2, 3, 4, 5. 1, 2, 3, 4. All right, we've done that. Draw a nonlinear function passing through the points above that is continuous on the closed interval and differentiable on the open interval. Right? So I have to make sure that I don't lift up the pencil, I don't have any gaps or breaks, and I have to make sure I have no cusps, no vertical tangent lines, no corners. Right? So I'm going to connect the two. There we go. So other than a little blip here, which is not supposed to be. Okay, there we go. That's pretty close. We want to draw a line between the points and calculate the slope. And I'm going to do that with the line tool. And then I'm going to move the line so it actually goes through the point. Right, so there's our line. And we're going to calculate the slope of the line. Right, so that's pretty easy because we have the point. Right, so the slope. And this would be the average rate of change. This is the slope of the secant line. Right, it's just the slope between any 2 points is the average rate of change. So that is a secant line. A secant line just connects 2 points on the curve. Right, that would be 4 minus a -4, so 4 plus 4, divided by -6 minus 5 would be -8/11. Are there any other points on your function where the tangent line has the same slope as the line joining -6, 4 and 5, -4? Sketch these tangent lines. Well, I'm going to clone this one, and looks like right here. Is there any others? No. Did I get no? I may have to. There we go. Oh, looks like there's one here too. Right here. All right, so looks like 2 places where the tangent line has the same slope. Right, so this first one, this one was the secant line. This one was a tangent line. It's only intersecting one time. This one here is also a tangent line. And we'll just call this one C1. And we'll just call this one C2. And mean value theorem relates to the slope of the secant line as related to the slope of the tangent line. Let's take a look at mean value theorem. Right, but you saw continuous, differentiable. I was able to find at least one place where the tangent line had the same slope as the secant line. So let's take a look at what mean value theorem says. And this one is in your notes. You can add the additional parts. Actually, you should. So Rawls' theorem, which we just learned about in the last video, is a special case of the mean value theorem. French mathematician Joseph Louis Lagrange, 1736 to 1813, first stated the next very important theorem. So mean value theorem, let f be a function that satisfies the following 2 hypotheses. F is continuous on the closed interval, f is differentiable on the open interval. Hey, that's what we just had for Rawls' theorem. Same two have to apply. This one only has two requirements, though. Then there is a number, x equals c, in AB, such that f prime of c, which is the slope of the tangent line, right? So f prime of c, that's the slope of the tangent line, right? We find the derivative, we plug in the value that we're interested in, and that gives us the slope of the tangent line at that value, equals the slope of the secant line. This is the slope of the secant line, right? This is the average rate of change, right? So if our function is continuous and if it is differentiable on an interval, then there has to be a value such that the slope of the tangent line is the exact same thing as the slope of the secant line, and which is what we just saw. In other words, the secant line is parallel to the tangent line. So it's guaranteed by mean value theorem, so long as the function is continuous and differentiable on an interval. All right, so here's some graphical implications. So here we have our secant line. I've marked that in, and you should too. And then we have a tangent line that has the exact same slope. In the second example, we have two tangent lines that have the exact same slope as the secant line, just like we did in my exploratory, exploratory example at the beginning of this lesson. And it didn't matter what I drew that to be. I had a different function last year. So long as it's continuous and differentiable, there has to be a place where the tangent line has the exact same slope as the secant line, and that's mean value theorem. All right, so here we have a real world connection. A plane begins its takeoff at 2 p.m. on a 2,500 mile flight. The plane arrives at its destination at 7:30 p.m. Ignore time zone changes. There was none. Explain why there were at least 2 times during the flight when the speed of the plane was 400 miles per hour. All right, so let's just take a look at this graphically, what this would look like. All right, so here we have on the x-axis we have time. On the y-axis we have distance. Right, and speed, ignoring direction. Right? The speed's always positive, but you don't have to worry in this case. Well, actually, you would. The velocity will not always be positive, but speed is always positive. So it's the absolute value of the distance divided by the time. Right? So in this case, speed is the absolute value of the distance divided by time, which is our average rate of change. All right, so let's take a look at from the start to the point. We'll find the average rate of change from the start to the beginning, but let's just think about how the plane goes, right? So the plane takes off. How fast does it go when it takes off? Well, before any time's gone by, it's going 0 miles an hour, isn't it? It's traveled 0 miles and no time has gone by. Right? And then it increases the time. The distance increases, right? Speed is increasing. And then speed, we have to do this, right? All right, so just imagine our little plane here, right? Has to take off, right? And then he has to land. Right, so his average rate of change is going to be, and maybe I shouldn't have put distance there, but because we're really just looking at speed. I want to look visually. Let me just put speed over time. We don't care about the distance. We care about the speed. So the speed over time, and the speed we'd find by taking how far it went and dividing by how long it took. But my graph here is actually just looking at the speed, right? Because the distance would keep on increasing. It's speed, right? He gets to its maximum speed. His maximum would be here, and then it has to land, and its speed is 0 again. Right? So here the speed is 0 when it lands and when it takes off. So I shouldn't have had distance over there. I really meant speed. I was thinking speed, not distance. Right? And so here somewhere it's its maximum, right? I don't know where that is, but somewhere it has a maximum speed. Let's calculate out its average rate of change. Move it over here, I'm running out of space. All right, so it goes 2,500 miles. Takes 5.5 hours to do that, right? From 2 o'clock to 7:30 would be 5.5 hours. All right, and that is about 454.54 miles, I think it was miles per hour. Yes, miles per hour. Yeah, what else would it go? I guess it could go kilometers per hour. All right, so let's think about this. So its starting speed was 0. If its average rate of change was 454.54, that means taking it from the beginning to the end, right? Taking it from the maximum to the minimum, right? The average was 454.54 miles per hour. That was the average over the whole interval. Its maximum speed has to be greater than 454.54 miles per hour. Speed is something that's continuous. And you can't skip values. You can't go from 10 to 20 and you skipped over 11, 12, 13, 14, 15, 16, 17, 18, 19. That's not possible. So let's call this one here 400. So if that were 400, maybe actually I want to make it a little bit less for my picture here. Notice that right here and right here, we'd have to be at 400 miles per hour. And every speed between, oops, that's too many E's in between, 0 and whatever the maximum is, which has to be greater than 454.54 miles per hour, has to be represented. And so this is kind of a real world example of mean value theorem, right? So and every single value, there has to be a tangent line. So for every value between 0 and greater than 454.54 has to be represented, right? Every value including 400 miles per hour has to be represented. So somewhere our secant line and our tangent line has to be 400 miles per hour if we choose the right interval. Right? Every value between our maximum and our minimum has to be represented. A little real world example. This one is in your notes completely with a couple little boo-boos. I typed in average value instead of average rate of change. Those are very, very, very different things. All right, so determine if the mean value theorem applies to f of x equals x cubed minus x on 0, 2. If so, find the values guaranteed by the theorem. All right, so first we want to check that it's continuous and differentiable, but this is a polynomial function and they are continuous and differentiable everywhere. All right, add that to your notes. All right, let's find f of a and f of b. Now, for mean value theorem, they do not have to be the same, right? But we're going to take those values and find the slope when we're done. All right, so f of a, and then find where's the tangent line equal that slope. All right, so f of a was 0. F of b, f of 2 is 6. So the average rate of change is going to be the difference in the y values divided by the difference in the x values. So 6 minus 0 divided by 2 minus 0 is 3. We find our derivative, right? Just use the power rule. F of x equals 3x squared minus 1. And we set the derivative equal to the average rate of change. because mean value theorem says if it's continuous and differentiable, somewhere on our closed interval, the slope of the tangent line is going to be exactly the same as the slope of the secant line. So the slope of the secant line is 3. Let's find where the tangent line is 3. So we're going to set our derivative equal to 3. We have 3 equals 3x squared minus 1. Let's just isolate the x, take a square root. All right, so we're going to add 1 to both sides, then divide by 3. So we have 4/3 equals x squared. We had 4/3 in the last video. And then when you take a square root, do not forget positive and negative. There are 2 solutions. If it's an even root, don't forget both of them. Right? Then we check, are they in the interval? Right? Our interval is from 0 to 2. So you can throw out the negative value. Negative square root of 4/3 is not in the interval. Square root of 4/3 does satisfy mean value theorem. And sometimes when you have a fraction in a radical, sometimes it begins to look like part of it's not in the radical. And that could be simplified, so maybe we should. All right, so we could change that so it was very, very clear by rationalizing square root of 4/3. You can rewrite that as the square root of 4 over the square root of 3. That's actually preferable to the square root of 4/3, which starts to look like the square root of 4 over 3. And then people will wonder why you didn't just make that 2/3. And in fact, it's not 2/3, it's the square root of 4/3. So the square root of 4/3 rationalized would be the square root of 12 over 3. I mean, that makes that pretty clear. I'd probably avoid putting fractions under a radical because they didn't always look very clear. All right, let's determine all the values C which satisfy the conclusion of the mean value theorem for the function. Right? So this is a polynomial function. Are continuous and differentiable everywhere. So we have satisfied the requirements for a mean value theorem. Right, so requirements for a mean value theorem satisfied. Right, so let's find so we have to find the average rate of change. Right, and so we need f of a and f of b. Right, so f of -1 is -1 cubed plus 2 times -1 squared minus a -1. So that's -1 plus 2 plus 1, so that's going to be 2. And then f of 2 would be 2 cubed plus 2 times 2 squared minus 2, so that would be 8. And then 2 squared is 4 times 2 is 8, minus 2, so that's going to be 14. So average rate of change is 14 minus 2 divided by 2 plus 1. So that would be 12 divided by 3, which is 4. All right, so now let's find the derivative. All right, so we have f prime of x is equal to, just power rule, 3x squared plus 4x minus 1. And we'll set that to the average rate of change. So we have 4 equals 3x squared plus 4x minus 1. Let's subtract 4 from both sides. 0 equals 3x squared plus 4x minus 5. And this is not factorable. I remember that. So, it's not factorable. We have 2 choices, completing the square or our quadratic formula. This is not the prettiest function for completing the square. If a was 1, that would be different. Or if b was even divisible by a, that would be fine too. Here we're going to solve using quadratic formula, because this is just not a pretty completing the square. So we have x is equal to -4, my shadow keeps blocking, plus or minus 4 squared minus 4 times 3 times -5, all divided by, all divided by 2 times 3. So -4 plus or minus 16, that would be plus 60 divided by 6. So -4 plus or minus the square root of 76 divided by 6. All right, so 76 is divisible by 4. -4 plus or minus, my 7 looks like a 2. All right, so I can factor out so if it's divisible by 4, I can factor out a 2, right? Square root of 4 is 2. And 19 would be left. Divided by 6, we could reduce. Boy, I need a lot of space here. So -2 plus or minus the square root of 19 divided by 3. All right, so those are the two values. So we have two values there. Are they both good? Plus square root of 19 over 3, and x equals -2 minus the square root of 19 over 3. Well, what was our interval? I don't know. I can't see it anymore. -1 and 2. What do you want to bet there's no, I don't think the second one is going to be in the interval. I feel pretty confident on that. Let's check the first one though. So, oops, come on. All right. We got square root of 19 minus 2 divided by 3. So this one here is approximately 0.7863, because there's lots of 9s after that. And so that is within the interval. This other one here, all right, so square root of 19. This time it's, oops, I put too many times in there. All right, do it again. Square root of 19 and minus 2 is clearly way out of the interval. It'd be -6.3589. So this one here is outside interval. So this, nothing's guaranteed if you're outside the interval, right? So this is value of x where the average rate of change equals the instantaneous rate of change as guaranteed by mean value theorem. I need like 3 pages for this one. I should have wrote smaller in the beginning. And we can abbreviate that MTV, or MVT. MTV is something different. All right? So we determined that requirements for mean value theorem were satisfied. We found the average rate of change. We took the derivative. We set it equal to the average rate of change, and we solved for x. So not the prettiest problem in the world, but I wouldn't say it's the most difficult either. For the following functions, determine if mean value theorem applies. If so, find the value of c guaranteed by the theorem. If not, specify why the theorem does not apply. Let's take a look at the first one. F of x equals x plus 5 divided by x minus 1 on negative 3, 5. Do you see what's wrong with this one? Well, if not, here it is. What can x equal? Can't equal 1. 1's in the interval. So since f of x is not continuous on negative 3, 5, there's a vertical asymptote at x equals 1. Mean value theorem does not apply. You have to meet the requirements. Got to be differentiable, got to be continuous and differentiable. First one's not continuous. Do you see the problem with the second one? G of x is continuous on negative 3, 3. Cube root functions are continuous everywhere. Actually, I'm just going to get rid of this shade here. But if you take the derivative, you can see that g of x is not differentiable on negative 3, 3. There's a vertical tangent line at x equals 0, right? Because the derivative would be g prime of x equals 2 divided by 3 cube roots of x. Well, you go and plug in 0 and you have a problem, right? So, not differentiable at 0, and it's a vertical tangent line. Right? So, can't use mean value theorem because the requirements are not met. Let f of x be a function that's differentiable for all x. Suppose f of 0 equals negative 3, and f prime of x is less than or equal to 5 for all values of x. How large can f of 2 possibly be? So I'm going to solve this out algebraically, and then we'll add a little graphically just to demonstrate. Right, so remember that, and this is for both of these problems, A and B, f prime of x is the slope of the tangent line. And so in A here, this one will be A. Notice it says that the tangent, the slope has to be less than or equal to 5. So that means the maximum slope is 5. It tells us that f of 0 equals negative 3. So we could start at x at negative 3, right? Because we're given that value. And when is the function equal to negative 3? When x is 0, right? So f of 0 equals negative 3. Right, so the change in y will be 5, because that's our maximum slope, for a change in x of 1, right? So every time I add 1 to x, I can add 5 to y, because our maximum slope is 5. So the change in y would be 10 for a change in x equaling 2. Right? And we want how large f of 2 would be. So x is changing by 2, y is going to change by 10. We're starting at negative 3, so negative 3 plus 10 would be 7. Right? So f of 2 is at most equal to 7. All right, so let's take a look at this graphically, right? So we're starting at 0, negative 3. So you can figure this out without the graph, right? But you can also use the, you can figure it out logically, or you can use the graph to help you out. All right, so we're starting at 0, negative 3. The maximum slope is 5. So that means we go up 5, 1, 2, 3, 4, 5, to the right 1. Right, well, we didn't get to, we want f of 2. Do it one more time. 1, 2, 3, 4, 5 to the right 1. And notice we got to the same place as I said we would algebraically. Right? So the most that we can be is 7. Right, let's look at the second one. Suppose that f of 5 is 2 and f prime of x is greater than or equal to negative 3 for all x. What is the largest possible value of f of 1? Well, f prime of x is greater than or equal to negative 3. Right? So our slope is negative. Right? So our maximum value occurs at the minimum slope, right, which is -3. That's the because we're going to actually be going the other direction, right? Because we're given f of 5. We're going to count backwards f of 1. Anything else, if it were -2, which is greater than -3, would mean a smaller change, right? -1 is greater than -3. That would be a smaller change. If we want the greatest change, because we're counting backwards, right, it's going to occur at our minimum slope, and that's because the slope is negative. Right, slope is negative. All right, so again, we'll start the same way. All right, so we're going to start at 2. Right, because make sure I don't get into the way here. I think, yeah, I'm okay. Let me move over just a little bit, because we're gonna show it on the graph too, and I don't want to get in the way of the graph. We'll start at 2 because f of 5 equals 2. Right, and so we have change in y is, so we're counting backwards, right? So a change in y is going to be 3 for change in x equaling -1, okay? Because we're going from a greater x value to a smaller x value. Change in y would be 6 for change in x equaling -2. Change in y equals 9 for a change in x equaling -3. And we're going from 5 to 1. So one more. Change in x equals 12 for a change in x. I'm writing my change and my x so close. Change in x equaling -4. Right? So we're going 4 back. All right, so that means we've got, what did we start at? 2. Plus 12 is going to give us 14. All right, let's see if that worked out for us. All right, with our graph. And what if we made a mistake, right? We'd probably catch it on our graph. All right, so we're starting off, we may have a hard time catching it on our graph because we're going to go right off the graph. But that's all right. I think we can still figure it out. So we're at f of 5 equaling 2. You think my problem would give me a better graph, huh? All right, so we would be going, if our slope is -3, right, we're going 3 up because we're going 1 to the left. So 1, 2, 3, and 1 to the left. 1, 2, 3, and 1 to the left. All right, so far we made it to 3, 8, right? And we're going to have to go 2 more times, right? So 1, 2, 3, and 1 to the left means this point here is 2, 11. And then we go up 1 more time, 3 up and 1 to the left, and that would be 114. All right, exact same value we got here algebraically. But here would be our line, and I'll just connect that. All right? All right, so it's really just a matter of thinking logically and kind of counting backwards. All right, so we're done with these two. Big takeaway, and then I have one problem. I have some questions at the end of the notes. Mean value theorem guarantees the existence of a tangent line that is parallel to the secant line through points A, f of A, and B, f of B, the endpoints of the interval. There must be a point on the open interval AB at which the instantaneous rate of change is equal to the average rate of change over the interval. So long as the requirements have been met, your function is continuous and differentiable on the interval. So continuous on the closed interval, differentiable on the open interval, right? And then we have a little qualifier here. If f prime of x equals 0 for all x in the interval ab, then f is constant on ab. Right? You have a constant function. Right? So there's our big takeaways for mean value theorem. Right? The big idea of this whole lesson. And let's do a few true-false questions. And I had this in your notes only, so I had to cut it and paste it from your notes. So if it looks a little pixelated, I'm sorry, but it's clear in your notes. All right, comprehension check, true or false. If f prime of c equals 0, then f has a local maximum or a local minimum at c. And actually, that is a false. It might not. This will only be true if f prime of x changes sign at x equals c. So that would be a false unless there's a sign change. Right? Because you could have a horizontal tangent and then just keep increasing or just keep decreasing. True or false, if f is differentiable and has a local maximum or minimum at x equals c, then f prime of c equals 0. And number 2 is true. Right? We don't have to worry about the continuity part if it's differentiable, because differentiability, that's a T, implies continuity. So if you're told the function is differentiable on the interval, it must be continuous on the interval. You know, I don't know if I can squeeze that in there. Oh, maybe. Continuity. There we go. So that says differentiability implies continuity. You know, here. I'm going to put it down here. This is for B. No, go away, go away, go away. We didn't want you. And let's make this look like a word. Right, C. A function continuous on an open interval may or may not have an absolute max or absolute minimum on that interval. I think I read this backwards, but it doesn't matter. Give an example of a continuous function on 0, 1 that has no absolute maximum. All right, so here's one that has no absolute max, no absolute min, or everything is the same. And that's the function y equals 1. Right? That one is continuous and does not have a max or min because everything is the same. Everything is 1. And true or false, if f is differentiable on the open interval ab and continuous on the closed interval, and f prime of x does not equal 0 for all x in ab, then we have f of a does not equal f of b. All right, so here, sort of looking at Rawls' theorem backwards, if f of a equals f of b, then, and we already established that it's differentiable and continuous, then somewhere f prime of c equals 0. And I'll just put here, actually I can't fit the word requirements in there, what I was thinking. Requirements for Rawls' theorem met, right? We already established that it was continuous and differentiable. So if f prime of c does not equal 0, well, then we must have not met the third requirement, which is f of a equaling f of b. So this is true, right? So if f of a does not equal f of b, then we're not guaranteed to have a place where where f prime of x is equal to 0. And if f prime of x never equals 0, well, then there's no way f of a equals f of b, because Rawls' theorem says if it's differentiable and it's continuous and f of a equals f of b, then somewhere f prime of c has to be 0. So if we're not meeting the results, we must not have met the one requirement, and that was that f of a equaling f of b. And that's the end of this particular podcast. Thanks for watching Mean Value Theorem. All right, so up next, we're going to be finding those relative max and min values in the first derivative test. Bye for now.